Hello there, and welcome to the Sleepless Astronaut channel. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight we're going to drift back through time, further than any human has ever traveled, to the very beginning of everything. To that first moment when there was nothing, and then suddenly, impossibly, there was something. Close your eyes if you haven't already. Feel the weight of your body against whatever surface holds you. Notice how solid everything feels, how real, how permanent. But none of it has always been here. Not the ground beneath you, not the air you breathe, not even the atoms that make up your body. All of it came from somewhere, all of it has a beginning, and that beginning is where we're going tonight. Let's start with what we know, or think we know. The universe is old. Unimaginably old. About 13.8 billion years have passed since it began. That's a number so large it loses meaning when you try to picture it. 13 billion years. Longer than the age of our sun, longer than the existence of our planet, longer than the entire history of life on Earth, multiplied many times over. But there was a time before all of that. A time before stars, before galaxies, before light itself could travel freely through space. A time so early and so extreme that the laws of physics, as we understand them, might not have even applied yet. We call that moment the Big Bang, though that name is a bit misleading. It wasn't an explosion in space. It was an expansion of space itself. Space and time and energy all erupting into existence together, from a state so compressed and so hot that we can barely describe it with our current understanding of reality. Imagine, if you can, everything that exists. Every star in every galaxy, every planet orbiting every sun, every particle of dust floating in the cosmic void, all the light that's ever been emitted, all the matter that's ever formed, all the dark, empty distances between celestial objects. Now imagine all of that squeezed down, compressed into something smaller than an atom, smaller than anything you could see with any microscope. All of existence packed into a space so tiny it makes a grain of sand look like a universe unto itself. That's where it all began, in that impossibly small, impossibly hot, impossibly dense point. Not a point in space because space didn't exist yet. Not a point in time because time itself hadn't started flowing. Just pure, concentrated existence on the edge of becoming. And then it happened. The universe began to expand. Not with a sound, because sound needs air to travel through, and there was no air yet. Not with light, because light couldn't exist in those first fractions of a second. Just expansion. Space itself growing, stretching, inflating at speeds that make light look like it's standing still. In the first tiny fraction of a second after the Big Bang, something extraordinary happened. We call it cosmic inflation. For a period of time so brief that it's hard to even comprehend, the universe doubled in size, over and over and over again. Not just growing, but exploding outward at rates that seem to violate everything we know about how fast things can move. In less than a trillionth of a trillionth of a trillionth of a second, the universe went from smaller than an atom to roughly the size of a marble. That might not sound impressive until you realize what it means. That's faster than the speed of light, far faster, which should be impossible. But it's not that things were moving through space faster than light. It's that space itself was expanding, carrying everything with it. And there's no speed limit on how fast space can grow. Why did this happen? What caused this sudden, violent inflation? Physicists believe it was driven by a strange kind of energy field, something that only existed in those earliest moments. An energy that pushed space apart with incredible force, like a spring that had been compressed for eternity suddenly being released. This field is called the inflaton field, and it existed in what we call a false vacuum state. Think of it like a ball sitting on top of a hill. It's stable for a moment, but it's not in its lowest energy state. Eventually, it has to roll down. When the inflaton field rolled down from its false vacuum state to its true vacuum state, it released an enormous amount of energy. That energy didn't just push space apart. It created space. It generated new space at an exponential rate, doubling the size of the universe every tiny fraction of a second. And then, just as suddenly as it started, inflation ended. The field decayed, its energy transformed into matter and radiation, into the fundamental particles that would eventually become everything we see today. The universe continued expanding, but at a more sedate pace, following the gentler expansion we observe today. This moment when inflation ended and the inflaton field's energy converted into particles, this is what we might call the hot Big Bang. This is when the universe as we recognize it truly began. Before inflation, the universe was cold and empty, just this strange energy field in a false vacuum state. After inflation, the universe was hot and dense and filled with energy and the seeds of matter. But let's slow down for a moment. Let's take a breath. Your breathing is steady now, calm and rhythmic. As you listen to this story of the universe's birth, feel your own body settling into rest. The universe began in violence and chaos, but it settled into order. You too are settling now from the chaos of the day into the peace of sleep. Now, in these first moments after inflation ended, the universe was filled with pure energy. The temperature was beyond anything we can truly comprehend. We're talking about temperatures of 10 to the 32 degrees Kelvin. That's a 1 followed by 32 zeros. At those temperatures, even the fundamental forces of nature, the forces that govern how particles interact, were unified into a single force. Today, we experience 4 fundamental forces. There's gravity, which holds planets in orbit and keeps your feet on the ground. There's electromagnetism, which makes magnets stick to refrigerators and allows light to travel through space. There's the strong nuclear force, which binds quarks together into protons and neutrons and holds atomic nuclei together despite the electromagnetic repulsion between positively charged protons. And there's the weak nuclear force, which is responsible for certain types of radioactive decay and plays a crucial role in how stars shine. These 4 forces are very different from each other. They operate at different scales, have different strengths, affect different particles in different ways. Gravity is incredibly weak compared to the others, but it operates over infinite distances. The strong force is immensely powerful, but only works over distances smaller than an atomic nucleus. Electromagnetism falls somewhere in between. The weak force is strange, operating at very short ranges but capable of transforming one type of particle into another. But physicists believe that in the extreme conditions of the earliest universe, these 4 forces were all aspects of a single unified force. They were different facets of the same underlying phenomenon, the way that ice and water and steam are all different states of the same substance. As the universe cooled, this unified force underwent what we call symmetry breaking. It split apart like a single note dividing into a chord. First, gravity separated from the other three forces. This happened incredibly early, perhaps during the inflationary epoch itself, when the universe was only 10 to the minus 43 seconds old. That's a decimal point followed by 42 zeros, and then a 1. A Planck time, the smallest meaningful unit of time in physics. At this moment, gravity became its own distinct force, following the curved geometry of space-time, as described by Einstein's general relativity. The other three forces remained unified for a bit longer, but not much longer. As the universe continued to cool and expand, the strong nuclear force separated next. This happened when the universe was perhaps 10 to the minus 35 seconds old. Now there were two distinct forces, gravity and the strong force operating independently, and electromagnetism and the weak force still unified in what we call the electroweak force. Finally, when the universe was about 10 to the minus 12 seconds old, a trillionth of a second after the Big Bang, the electroweak force split into electromagnetism and the weak nuclear force. Now all four fundamental forces were distinct and separate, operating according to the rules we observe today. This symmetry breaking is one of the most important processes in the early universe. It's what allowed the universe to become interesting, to develop structure, to evolve complexity. If the forces had remained unified, if symmetry had been preserved forever, the universe would be a very boring place. No atoms could form, no chemistry could happen, no stars could ignite, no life could emerge. Just a uniform sea of energy, unchanging for eternity, perfect in its symmetry, but utterly sterile. But symmetry broke, the forces separated, and as the universe continued to cool, particles began to emerge from the energy. First, the most fundamental particles we know of, quarks and leptons, the building blocks of all matter. These particles didn't last long in isolation. The universe was still far too hot and dense for them to exist peacefully on their own. Quarks, in particular, cannot exist alone in nature. They're always bound together in groups by the strong nuclear force. In the early universe, quarks and antiquarks and gluons, the particles that carry the strong force, formed a state of matter we call a quark-gluon plasma. It was a roiling, seething ocean of fundamental particles, so hot and dense that individual protons and neutrons couldn't form yet. And there was antimatter. This is crucial to understand. For every particle that formed, an antiparticle formed as well. An electron and a positron, its antimatter twin, identical in mass but opposite in electrical charge. A quark and an antiquark. Matter and antimatter are like mirror images of each other, and when they meet, they annihilate completely, converting back into pure energy, according to Einstein's famous equation, E equals mc squared. In the early universe, matter and antimatter were created in equal amounts, and they were constantly annihilating each other. A particle and antiparticle would meet, destroy each other in a flash of energy, and that energy would immediately create a new particle-antiparticle pair. It was a dynamic equilibrium, creation and destruction, happening simultaneously at an unimaginable rate, the universe flickering between matter and energy faster than thought. But there was a slight asymmetry. a tiny, crucial imbalance in the laws of physics. For every billion antiparticles created, there were 1,000,000,001 particles. Just one extra particle for every billion particle-antiparticle pairs. An asymmetry of 1 part in a billion. Now, 1 part in a billion might not sound like much. It's an incredibly tiny difference. But that tiny imbalance made all the difference. It's the reason you exist. It's the reason anything exists. As the universe cooled and expanded, the energy density dropped. Eventually, around 1 microsecond after the Big Bang, there wasn't enough energy to create new particle-antiparticle pairs anymore. The creation stopped, but the annihilation continued. Particles and antiparticles found each other and destroyed each other, converting back to energy in brilliant flashes of gamma rays until almost all of them were gone. Almost all. But not quite all. Because of that tiny asymmetry, that 1 extra particle for every billion antiparticles, there was a small amount of matter left over after all the antimatter had found partners to annihilate with. That leftover matter, that cosmic remainder, is everything we see today. Every star and every galaxy, every planet, every moon, every asteroid, every atom in your body, every breath you take, every thought you think. All of it exists because of a 1 in a billion asymmetry in the first microsecond after the Big Bang. If the universe had been perfectly symmetric, if matter and antimatter had been created in exactly equal amounts, they would have completely annihilated each other. The universe today would be nothing but light, photons spreading through empty space, with nothing to illuminate, no matter anywhere. No stars, no planets, no chemistry, no life, no consciousness. No you listening to this, no me telling this story. Just an ocean of light expanding through the void forever. The fact that you exist, that anything exists, is because of this tiny violation of symmetry. And we don't fully understand why. We know the asymmetry is there. We can measure its effects with extraordinary precision. But we don't know what fundamental principle of physics creates this imbalance. We don't know why the universe chose matter over antimatter. We don't know why there's something rather than nothing. Perhaps it's built into the fundamental laws of physics in a way we haven't discovered yet. Perhaps there's a deeper symmetry we don't understand that mandates this asymmetry at lower energies. Or perhaps it's random, a quantum fluctuation in the earliest moments that happen to favor matter over antimatter in our particular region of space. If the multiverse is real, if there are other bubble universes beyond our own, perhaps some of them favor antimatter instead. Perhaps some maintain perfect symmetry and remain sterile and empty. We don't know. But we know that in our universe, matter won. And because matter won, we're here. Take a deep breath now. Feel the air entering your lungs, oxygen molecules that were created in stars billions of years ago, now giving you life. Feel your body relaxing deeper into rest. The story we're telling is vast, stretching across billions of years and unimaginable distances, but you are part of it. You are here now, connected to it all. Let's drift forward in time. The universe is now about 1 microsecond old. The quark gluon plasma is beginning to cool enough for quarks to bind together permanently. They combine in groups of 3 to form protons and neutrons, the particles that will eventually make up the nuclei of atoms. 2 up quarks and 1 down quark make a proton. 1 up quark and 2 down quarks make a neutron. These combinations are held together by the strong nuclear force, carried by gluons that zip back and forth between the quarks, binding them tightly. At this point, the universe is filled with a hot soup of protons, neutrons, electrons, neutrinos, and photons, all bouncing off each other in a frenzy of collisions. The temperature is still trillions of degrees, far too hot for protons and neutrons to stick together and form atomic nuclei. Any time they try, the ambient energy tears them apart again. But the universe keeps expanding, and as it expands, it cools. By the time the universe is about 1 second old, it's cooled to about 10 billion degrees. Still incredibly hot by any human standard. Hotter than the core of any star today, but cool enough for something important to happen. Neutrinos, ghostly particles that barely interact with anything, decouple from the rest of the matter. They stop colliding with other particles and begin traveling freely through space. Those neutrinos are still out there, forming a cosmic neutrino background, similar to the cosmic microwave background, but even older and even harder to detect. And now, a few minutes after the Big Bang, the universe is cooled to about 1 billion degrees. Finally, it's cool enough for protons and neutrons to stick together. Nuclear fusion begins, not inside stars because there are no stars yet, but throughout the entire universe. This is Big Bang nucleosynthesis, one of the most important events in cosmic history, and it lasts for only about 17 minutes. During these 17 minutes, protons and neutrons collide and fuse together, building up the nuclei of the lightest elements. 2 protons and 2 neutrons combine to form helium-4, the most common isotope of helium. A single proton is hydrogen. A proton and a neutron together make deuterium, heavy hydrogen. 2 protons and a neutron make helium-3. 3 protons and 4 neutrons create lithium-7. The process is self-limiting. As the universe expands and cools, the temperature drops below the threshold needed for fusion. By the time the universe is about 20 minutes old, it's too cool for nuclear fusion to continue. Big Bang nucleosynthesis ends, and the nuclear composition of the universe is set for hundreds of thousands of years to come. And what is that composition? About 75% hydrogen, 25% helium, and just tiny traces of deuterium, helium-3, and lithium. That's it. 3 elements, maybe 4 if you count deuterium separately. Everything else, every other element in the periodic table, had to wait. Carbon, nitrogen, oxygen, iron, gold, uranium, all the elements that make planets and life possible. None of them existed yet. They would have to be created later inside stars through billions of years of stellar alchemy. But that ratio, 3 parts hydrogen to 1 part helium, is one of the great confirmations of the Big Bang theory. When we look at the composition of the universe today, measuring the abundance of elements in gas clouds and ancient stars, we find exactly this ratio: 75% hydrogen, 25% helium. It's precisely what we'd expect if the universe started hot and dense and then cooled and expanded. If stars were responsible for all the helium in the universe, the ratio would be different. Stars create helium, yes, but not nearly enough to explain what we observe. Only the Big Bang, only those 17 minutes of primordial nucleosynthesis can account for the helium abundance we see throughout the cosmos. So we have nuclei now, hydrogen and helium nuclei, along with trace amounts of deuterium and lithium. But we still don't have atoms. We won't have atoms for a long time yet, not for hundreds of thousands of years. because the universe is still too hot for electrons to be captured by nuclei and settle into stable orbits. Anytime an electron tries to bind to a nucleus, a passing photon knocks it loose again. The universe during this time is a plasma, a state of matter where electrons are stripped away from nuclei and move freely. It's the fourth state of matter, after solid, liquid, and gas. In a plasma, electrical charges move independently, and the material behaves very differently than ordinary matter. The sun is made of plasma. Lightning is a plasma. And for hundreds of thousands of years after the Big Bang, the entire universe was a vast, expanding ocean of plasma. Light cannot travel freely through a plasma. Photons, particles of light, constantly scatter off the free electrons. A photon moves a tiny distance, hits an electron, bounces in a new direction, moves a tiny distance, hits another electron, bounces again, over and over, endlessly. Light is trapped, unable to travel more than a minuscule distance before being absorbed and re-emitted. The universe during this epoch is opaque. If you could somehow be there with eyes to see, you wouldn't see anything. Just a bright, glowing fog in every direction. A wall of light that you couldn't see through, no matter how hard you tried. But you're not there. You're here now, safe and comfortable, lying in the darkness, your eyes closed, your breathing slow and deep. And as you listen to this story of ancient times, feel yourself drifting, floating gently backward through time, watching the universe evolve from that initial moment of creation toward the cosmos we inhabit today. The universe expands and cools for 380,000 years. That's a long time by human standards, but it's less than 1/100% of the universe's current age. It's an eye blink in cosmic time. But during that eye blink, the universe is dark, not because there's no light, but because light can't travel. It's trapped, bound up with matter, scattered endlessly by free electrons. And then, finally, when the universe is 380,000 years old, it cools to about 3,000 degrees Kelvin, still hotter than the surface of most stars today, hotter than any fire you've ever felt, but cool enough for a phase transition to occur. Electrons, which have been zipping around freely all this time, start to settle into orbits around nuclei. Hydrogen atoms form as electrons bind to protons. Helium atoms form as electrons settle around helium nuclei. Atomic matter, neutral matter, emerges for the first time since the earliest moments after the Big Bang. This event is called recombination, though that's a bit of a misnomer because it's not actually a recombination. Electrons and nuclei had never been combined before this, but the name stuck, and now it's the standard term. Recombination is one of the most important moments in cosmic history because it's the moment the universe becomes transparent. When electrons are bound into atoms, photons no longer scatter off them nearly as much. Light is suddenly free to travel. Photons that had been trapped, bouncing endlessly between free electrons for hundreds of thousands of years, are suddenly released. They stream out across the universe, and they've been traveling ever since, for 13.8 billion years, crossing the entire observable universe. We can still see those photons today. We detect them with radio telescopes and microwave detectors as a faint glow that comes from every direction in space. We call it the cosmic microwave background, the CMB, and it's the oldest light in the universe. It's the afterglow of the Big Bang itself. stretched and cooled by billions of years of cosmic expansion from visible light into microwaves. When you look at the cosmic microwave background, you're seeing the universe as it was just 380,000 years after it began. You're looking back in time to recombination, to the moment when the fog cleared and light could finally travel freely. You're seeing the babied picture of the universe, the oldest photograph that exists or can ever exist. And what do we see in that ancient light? We see a nearly perfect uniformity. The temperature of the cosmic microwave background is almost exactly the same in every direction. 2.7 Kelvin, just a few degrees above absolute zero, the same temperature everywhere we look. This tells us that the early universe was incredibly smooth, incredibly uniform, with matter and energy spread almost evenly throughout space. But not perfectly evenly. There are tiny variations, small differences in temperature from one region to another. These differences are minuscule, just a few parts in 100,000. But they're there, and they're incredibly important, because those tiny temperature variations correspond to tiny density variations in the matter of the early universe. Some regions were slightly warmer, slightly denser, with a bit more matter than average. Other regions were slightly cooler, slightly less dense, with a bit less matter. And those tiny variations, those quantum fluctuations that were created during the inflationary epoch and stretched to cosmic size and frozen into the fabric of space, those are the seeds of all the structure we see in the universe today. Galaxies, clusters of galaxies, vast filaments and voids that make up the cosmic web, all of it grew from those tiny ripples in the cosmic microwave background. Because gravity amplifies differences. It's a feedback mechanism, a runaway process. Where the early universe was slightly denser, gravity pulled in more matter. Those regions became denser still, and their gravity grew stronger, pulling in even more matter. Over millions of years, over hundreds of millions of years, those tiny ripples grew into enormous clouds of hydrogen and helium gas, clouds hundreds of thousands or millions of times more massive than our sun. Meanwhile, the less dense regions became voids. Matter flowed out of them, pulled by the gravity of the denser regions nearby. The universe went from being almost perfectly smooth to developing structure, a cosmic web of filaments and sheets and clusters separated by vast empty voids. But it happened slowly. For hundreds of millions of years after recombination, the universe was dark. There were no stars yet, no galaxies, no light sources of any kind except the gradually fading afterglow of the Big Bang itself. This period is called the Cosmic Dark Ages, and it's one of the most mysterious epochs in cosmic history because we can't observe it directly. The light from that era is too faint and too redshifted for our telescopes to detect. We know what must have been happening, though. We can infer it from the physics and from observations of later times. Those vast clouds of hydrogen gas were slowly collapsing under their own gravity. As they collapsed, they fragmented into smaller clouds, which collapsed further, fragmenting again in a hierarchical process. Larger structures breaking down into smaller structures, each one growing denser at its core as gravity pulled matter inward. And in the hearts of those collapsing clouds, in the densest cores of the smallest fragments, the temperature and pressure were rising. As gas falls inward under gravity, it compresses. And when you compress a gas, it heats up. This is why a bicycle pump gets warm when you use it. You're compressing air, and compression creates heat. The cores of these collapsing gas clouds were heating up, slowly but inexorably, from the gravitational energy of their collapse. Higher and higher the temperature climbed, denser and denser the cores became. And then, somewhere between 100 million and 400 million years after the Big Bang, in one of these collapsing clouds, the core reached a critical threshold, 10 million degrees Kelvin. That's the temperature needed for nuclear fusion to begin, for hydrogen nuclei to overcome their electrical repulsion and slam together hard enough to merge. In that cloud and that core, hydrogen fusion ignited. Energy began pouring out from the fusion reactions, creating an outward pressure that balanced the inward pull of gravity. The collapse stopped. A star was born, the first star, the first light since recombination. After hundreds of millions of years of darkness, there was a point of brilliance in the cosmic void. Can you imagine that moment? After eons of silence and darkness, after the universe had cooled and emptied and become a vast, expanding space filled with nothing but invisible hydrogen clouds, suddenly there was light. A star, shining in the darkness, burning through nuclear fusion, converting hydrogen into helium and pouring energy out into the void around it. That first star was probably nothing like our sun. It formed from pure hydrogen and helium, with no heavier elements at all, because heavier elements didn't exist yet. And that made a difference. Heavy elements help gas clouds cool and collapse. Without them, a cloud has to be much more massive to collapse enough for fusion to start. The first stars were likely giants, perhaps hundreds of times more massive than our sun, burning bright and hot and blue-white, with surface temperatures of 100,000 degrees. They lived fast and died young. A star's lifetime is inversely proportional to its mass. Massive stars burn through their fuel quickly, while small stars can burn for trillions of years. These first-generation stars, what astronomers call population 3 stars, probably lasted only a few million years before exhausting their hydrogen fuel and dying in spectacular supernova explosions. But in their brief lives, they changed everything. They created the first heavy elements. Inside their cores, hydrogen fused into helium, then helium into carbon, carbon into oxygen, oxygen into neon, and so on up the periodic table. Each fusion reaction requires higher temperatures, more extreme conditions. The star's core contracts and heats up, allowing the next stage of fusion to begin. In the most massive stars, this process continues all the way to iron. Silicon fuses into iron, building up an iron core at the star's center, and then fusion stops. Because iron is special. Iron is the most stable nucleus. Fusing iron requires energy instead of releasing it. There's no energy source to support the star anymore. The core can no longer resist the crushing weight of the outer layers. What happens next is one of the most violent events in the universe. The iron core collapses catastrophically, falling inward faster than the speed of sound, compressing from the size of the Earth to the size of a city in less than a second. The infalling matter rebounds off the ultra-dense core in a shock wave that rips through the star's outer layers, blasting them into space at a significant fraction of the speed of light. A supernova, an explosion so bright it can briefly outshine an entire galaxy. And in that explosion, in those extreme conditions of temperature and pressure and neutron density, the heaviest elements are formed. Gold, platinum, uranium, all the elements heavier than iron, created in the death throes of massive stars and scattered into space. That first generation of stars died, and their deaths seeded the cosmos with heavy elements. Carbon, oxygen, nitrogen, iron, all the elements they'd created through fusion, plus the even heavier elements created in their final explosions, all scattered into space, mixing with the hydrogen and helium that was already there. And from those enriched clouds, a second generation of stars could form. Smaller stars, longer-lived stars, stars more like our sun. And around those stars, from the disks of gas and dust that surrounded them, planets could form. Rocky planets made of silicon and iron and magnesium. Planets with atmospheres of nitrogen and oxygen. Planets where water could exist as a liquid, where complex chemistry could happen, where life might eventually emerge. This is the cosmic cycle, the wheel of stellar birth and death. Stars are born from clouds of gas and dust. They live, fusing lighter elements into heavier ones in their cores. They die, returning those elements to space in gentle stellar winds or violent supernova explosions. New stars form from the enriched material, and the cycle continues. Each generation of stars adds more heavy elements to the cosmic mix, increasing the chemical complexity of the universe. By about 1 billion years after the Big Bang, this process was well underway. Stars were forming throughout the universe, in groups and clusters that were beginning to organize into the first galaxies. These early galaxies were smaller and more irregular than the grand spiral and elliptical galaxies we see today. They were chaotic collections of stars and gas, colliding and merging with each other, gradually building up into larger structures. And at the centers of many of these early galaxies, something strange was happening. Matter was falling into incredibly dense, incredibly massive objects that had formed from the gravitational collapse of giant gas clouds, or perhaps from the remnants of the very first generation of stars, black holes. Supermassive black holes, millions or even billions of times the mass of the sun, forming at the hearts of galaxies. As matter falls into a black hole, it doesn't just disappear quietly. It forms a swirling disk around the black hole, an accretion disk where gas and dust spiral inward, heating up through friction to millions of degrees. These accretion disks shine brilliantly, sometimes outshining all the stars in the galaxy combined. We call these objects quasars, and they're among the brightest objects in the universe. The early universe was full of quasars, massive black holes feeding on abundant gas and shining like beacons across cosmic distances. We can see them today, or rather we can see them as they were billions of years ago, because their light has taken billions of years to reach us. When we look at a quasar 10 billion light years away, we're seeing it as it was 10 billion years ago, when the universe was less than a quarter of its current age. Over billions of years, galaxies continued to grow and evolve. They merged with each other, combining their stars and gas into larger galaxies. They formed new stars from the gas they contained, gradually converting their hydrogen and helium into heavier elements. They expelled gas in vast outflows driven by supernova and by the energy from their central black holes. They pulled in new gas from the intergalactic medium, fresh fuel for star formation. And through all of this, gravity was organizing matter on the largest scales. Galaxies were drawn together into groups and clusters. Clusters were drawn together into superclusters. And between the superclusters, vast voids opened up, regions of space where galaxies were rare or absent entirely. This is the cosmic web, the large-scale structure of the universe, a foam-like pattern of dense filaments and walls surrounding empty voids. But there's something strange about the cosmic web. The gravity from the stars and gas and black holes that we can see, the ordinary matter made of protons and neutrons and electrons, isn't strong enough to explain the structure we observe. Galaxies are rotating too fast. They should fly apart, but they don't. Galaxy clusters are moving too fast relative to each other. They should disperse, but they don't. The cosmic web holds together more strongly than it should. The only explanation is that there's more matter out there than we can see. Invisible matter. Matter that doesn't emit light, doesn't absorb light, doesn't interact with light or with ordinary matter in any way except through gravity. We call it dark matter, and it makes up about 85% of all the matter in the universe. Everything we can see, all the stars and galaxies and gas clouds, all the ordinary matter made of atoms, that's only 15% of the total matter content of the cosmos. We don't know what dark matter is. We've never detected a dark matter particle directly, despite decades of searching with increasingly sensitive detectors. We know it's there because we can see its gravitational effects. We can measure how it bends light from distant galaxies. We can observe how it affects the rotation of galaxies and the motion of galaxy clusters. We can see its influence on the cosmic microwave background and on the formation of structure in the early universe. But we don't know what it's made of. Is it a new kind of fundamental particle, something not included in the standard model of particle physics? Is it a massive weakly interacting particle, a WIMP, that was created in the Big Bang and has been floating through space ever since, invisible and untouchable? Is it primordial black holes formed in the early universe rather than from collapsing stars? Is it something even stranger, like modifications to the law of gravity that make it behave differently on large scales? We don't know. Dark matter is one of the great mysteries of modern cosmology, a reminder that for all we've learned about the universe, there's still so much we don't understand. And dark matter isn't the only mystery. There's also dark energy. This is even stranger than dark matter. In the late 1990s, astronomers made a shocking discovery. They were measuring the brightness of distant supernovae, trying to determine how fast the universe's expansion was slowing down due to gravity. Everyone expected the expansion to be slowing. Gravity pulls matter together, so the expansion should be decelerating over time. But that's not what they found. The expansion wasn't slowing down. It was speeding up. Distant galaxies were receding faster than they should be, faster than could be explained by the initial expansion from the Big Bang. Something was pushing space apart, counteracting gravity, accelerating the expansion. We call this something dark energy, and we have no idea what it is. It makes up about 68% of the total energy content of the universe. Dark matter is 27%. Ordinary matter, everything we can see and touch, everything we're made of, is only 5%. 95% of the universe is dark, invisible, mysterious. Dark energy behaves like a property of space itself, a kind of vacuum energy that doesn't dilute as the universe expands. As space expands, more space is created, and with it, more dark energy. The more the universe expands, the more dark energy there is, and the faster the expansion accelerates. It's a runaway process that will shape the universe's ultimate fate. Because of dark energy, the universe will not recollapse in a big crunch. It will expand forever, faster and faster, stretching space itself until galaxies beyond our local group recede from us faster than light. Not because they're moving through space faster than light, but because space itself is expanding faster than light can cross it. Eventually, billions of years from now, we'll only be able to see our own local group of galaxies. Everything else will have been carried beyond our cosmic horizon by the expansion of space. And in the far, far future, trillions of years from now, even the stars in our local group will die. Star formation will cease as the available hydrogen is used up. The last stars will flicker out, leaving behind white dwarfs and neutron stars and black holes floating through an ever-expanding void. Those stellar remnants will slowly evaporate as protons decay, if they do decay, which we think they might over timescales of 10 to the 34 years or longer. Even black holes will eventually evaporate through a process called Hawking radiation, a quantum effect that allows them to slowly radiate away their mass over unimaginably long timescales. A solar mass black hole would take 10 to the 67 years to evaporate. A supermassive black hole would take even longer, but given enough time, even they will disappear. In the end, in the ultimate far future, the universe will be cold and dark and essentially empty. Just a thin soup of fundamental particles and radiation spread across an ever-expanding space, too far apart to ever interact with each other again. The universe will reach a state of maximum entropy, maximum disorder, where nothing can happen anymore because there are no energy gradients left to drive any processes. This is called the heat death of the universe, and it's the most likely ultimate fate of the cosmos. But that's trillions upon trillions of years in the future, so far ahead that it might as well be infinite. For now, for the next many billions of years, the universe is alive and vibrant. Stars are forming, planets are orbiting, life is evolving, and intelligent beings are looking up at the night sky and asking how it all began. We've come so far in understanding. Just a century ago, we didn't even know that other galaxies existed beyond the Milky Way. We thought our galaxy was the entire universe. We had no idea the universe was expanding, no conception of the Big Bang, no understanding that we're made of atoms forged in the cores of ancient stars. Now we know the age of the universe to within 1%. 13.8 billion years. We've measured the cosmic microwave background and decoded its patterns, reading the baby picture of the cosmos and learning about conditions just 380,000 years after the beginning. We've detected gravitational waves from colliding black holes and neutron stars, confirming Einstein's century-old predictions about the ripples in space-time. We've found thousands of planets around other stars, worlds as diverse as anything in science fiction. But there's still so much we don't know. We don't know what dark matter is. We don't know what dark energy is. We don't know if the universe is infinite or finite. We don't know if there are other universes beyond our own. We don't know what, if anything, existed before the Big Bang. We don't know why the laws of physics are the way they are, or if they could have been different, or if they are different in other regions of a vast multiverse we can never observe. These are humbling questions. They remind us that despite all our progress, we're still in the early days of understanding. The universe is vast beyond imagining, and our knowledge, while impressive, is still a small island in an ocean of mystery. But let's go back to that deepest question. What came before the Big Bang? Did time have a beginning, or does it extend infinitely into the past? Is our universe the only universe, or is it one of many? According to general relativity, Einstein's theory of gravity and space-time, time and space are not separate things. They're woven together into a single four-dimensional fabric called space-time. And the Big Bang is a singularity in that fabric, a point where the mathematics of general relativity breaks down, where density and temperature become infinite, and our equations stop making sense. At a singularity, the concept of before becomes meaningless. Time itself begins at the Big Bang. There is no prior moment because time doesn't exist yet. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because there is no north of the North Pole. All directions from the North Pole are south. Similarly, all moments of time are after the Big Bang. There is no before. That's one answer, and it's consistent with general relativity. But we know general relativity isn't a complete story. It describes gravity beautifully on large scales, the motion of planets and stars and galaxies. But it breaks down at the quantum level, at the scale of atoms and particles. And we need quantum mechanics to understand what happens in the extreme conditions near the Big Bang singularity. The problem is we don't have a complete theory of quantum gravity. We don't have a theory that successfully combines general relativity and quantum mechanics. String theory is one candidate. Loop quantum gravity is another. But neither is proven, and neither makes predictions we can currently test. So when it comes to understanding the very beginning, the Planck era, when the universe was younger than 10 to the minus 43 seconds, we're stuck with speculation. But it's informed speculation based on extrapolating our best theories, and several fascinating possibilities emerge. One idea is that the universe really did come from nothing, not from empty space because space is something, but from absolutely nothing. No space, no time, no energy, no matter, no laws of physics. True nothingness. How can something come from nothing? It seems to violate the most basic intuition we have about cause and effect. But quantum mechanics has shown us that reality is far stranger than our intuitions. In quantum mechanics, there's the Heisenberg uncertainty principle, which says that certain pairs of properties cannot both be known precisely at the same time. Energy and time are such a pair. Over very short time periods, the uncertainty in energy becomes very large. Energy can fluctuate wildly. In the quantum vacuum, particle-antiparticle pairs constantly pop into existence, borrow energy from the vacuum, exist for a brief moment, and then annihilate, returning the borrowed energy. These virtual particles are real in the sense that they have measurable effects. The Casimir effect and Hawking radiation are both consequences of virtual particles. Now, normally these quantum fluctuations are small. They create particles that exist for only a tiny fraction of a second before disappearing. But what if, under the right conditions, a quantum fluctuation could become permanent? What if the uncertainty in energy could be large enough to create not just a particle, but an entire universe? Some physicists, like Alexander Vilenkin and Stephen Hawking, have suggested that this is exactly what happened, that the universe is a quantum fluctuation that became real, that in the timeless, spaceless void before the Big Bang, quantum uncertainty allowed a tiny bubble of space and energy to spontaneously appear, and that bubble, through cosmic inflation, grew into everything we see today. In this view, the universe doesn't need a cause. It's a quantum event, and quantum events are inherently probabilistic. They don't have causes in the traditional sense. An electron can quantum tunnel through a barrier without a reason. A radioactive nucleus can decay without a cause, and a universe can pop into existence from nothing without anything making it happen. It's a strange idea. The entire universe has a quantum accident, but it's consistent with the laws of physics as we understand them, and it provides an answer to the question of where the universe came from without requiring anything external to the universe. Another possibility is that our universe isn't the only one, that the Big Bang wasn't the beginning of everything, just the beginning of our local region of reality. This is the multiverse hypothesis, and it comes in several different versions. One version arises naturally from cosmic inflation. Remember that inflation is driven by an inflated field in a false vacuum state. When that field decays to its true vacuum, inflation ends and the hot Big Bang begins. But the decay doesn't happen everywhere at once. It happens in some regions first, creating bubbles where inflation has ended, while in other regions, inflation continues. Those bubbles are separate universes, each with its own Big Bang, each expanding and evolving independently, and the inflating space between them continues to expand exponentially, creating more space in which more bubbles can form. It's an eternally self-reproducing process. Once inflation starts somewhere, it never completely stops. It ends in localized regions, creating bubble universes, but the overall inflating space continues forever, constantly spawning new bubbles. In this picture, our universe is just one bubble in an infinite foam of universes. Each bubble is causally disconnected from the others, separated by regions of eternally inflating space. We can never see beyond our bubble. We can never communicate with or visit the other universes. But mathematically, if inflation is the correct theory of the early universe, this multiverse might be inevitable. And here's where it gets even stranger. The laws of physics in each bubble universe might be different. During the phase transition when inflation ends, the way the fields settle into their final state might vary from bubble to bubble. The masses of particles, the strengths of forces, the number of dimensions of space, all of these might be determined by how the fields happen to settle when inflation ended. Each universe gets a different set of physical laws, randomly chosen from a vast landscape of possibilities. In some universes, the forces might be so different that atoms can't form. In others, stars might not be able to ignite. In others still, the expansion might be so fast that galaxies never form. Most universes would be sterile and lifeless, but in a tiny fraction of them, by sheer chance, the laws of physics would allow for complexity and structure, and maybe even life. We, of course, can only exist in one of those rare universes where the laws allow for our existence. This is called the anthropic principle. It's not that the universe was designed for us. It's that we can only observe a universe capable of producing observers. If the multiverse is real and the laws vary from universe to universe, then we necessarily find ourselves in one of the universes with life-friendly laws, no matter how improbable such a universe might be. It's a controversial idea. Some physicists love it. Others hate it. It's hard to test because we can't observe other universes, but it provides a possible explanation for why the laws of physics in our universe seem so finely tuned for life. Maybe they're not specially tuned. Maybe they're just randomly selected, and we exist in one of the rare universes where the random selection happened to allow for complexity. Yet another version of the multiverse comes from quantum mechanics itself. This is the many worlds interpretation proposed by Hugh Everett in the 1950s. According to standard quantum mechanics, particles exist in superposition states, being in multiple states at once until they're measured. When you measure a particle's position, for example, its wave function collapses and it takes on a definite position. But what causes the collapse? Why does measurement force the particle to choose? Everett suggested that maybe it doesn't choose. Maybe all the possibilities actually happen, but in different branches of reality. Every time a quantum event occurs, every time a measurement happens, the universe splits into multiple copies, one for each possible outcome. In one branch, you measured the electron at position A. In another branch, you measured it at position B. Both branches are equally real, but they can never interact with each other. You exist in all the branches, or rather, versions of you exist in all the branches, each one experiencing a different outcome of every quantum event. If this is true, then there are countless parallel universes, constantly branching and splitting with every quantum measurement. And quantum measurements are happening all the time, everywhere. Every particle interaction, every photon absorbed, every atom decaying, all of these are quantum events that cause the universe to branch. It's a dizzying thought. An infinite number of you, living slightly or dramatically different lives in an ever-branching tree of parallel realities. In some branches, you made different choices. In some, history unfolded differently. In some, the laws of physics might even be different if quantum events in the very early universe affected how the forces crystallized out. We don't know if the many worlds interpretation is correct. It's one way of understanding quantum mechanics, but it's not the only way. The Copenhagen interpretation says the wave function really does collapse, though it doesn't explain why or how. Other interpretations invoke hidden variables or objective collapse mechanisms. We don't know which, if any, is the true description of reality. But all of these ideas, the quantum creation from nothing, the eternal inflation multiverse, the many worlds interpretation, they're serious scientific hypotheses. They emerge from our best attempts to understand the deepest nature of reality, to extend our theories into realms we can't directly observe. And then there's another idea, even more speculative. What if the Big Bang wasn't the ultimate beginning? What if it was just a transition, a bounce from a previous state? Some approaches to quantum gravity suggest that when you account for quantum effects properly, the Big Bang singularity disappears. Instead of the universe compressing down to an infinitely small point, it reaches a minimum size, incredibly tiny, but not zero, and then bounces. This is called the Big Bounce. In this scenario, our universe might have been preceded by another universe, one that was contracting under its own gravity. As it contracted, it grew denser and hotter, approaching but never reaching a singularity. Instead, quantum effects created a repulsive force that stopped the collapse and reversed it into an expansion. That expansion is what we call the Big Bang. If the Big Bounce is real, then time extends infinitely into the past. There was no beginning. Instead, there's an eternal cycle of expansion and contraction, bounce after bounce, each cycle perhaps lasting trillions of years, but all connected in an infinite chain. Or perhaps, as strange as it sounds, our universe emerged from the interior of a black hole in another universe. Black holes are singularities where space-time curves so extremely that our equations break down. But what if, from the inside, a black hole looks like an expanding universe? What if the singularity at the center of a black hole and the singularity at the Big Bang are the same kind of thing, just viewed from different perspectives? In this model, every black hole that forms in our universe might be a doorway to a new baby universe, expanding away in its own separate space-time, forever disconnected from ours. And our universe might itself be the interior of a black hole in some parent universe, which is itself inside a black hole in another universe, an infinite nested hierarchy of universes within universes. These ideas might sound like science fiction. Maybe they are, maybe we'll never know which, if any, is correct. The beginning of the universe, or what came before the beginning, might be forever beyond our ability to observe or test. But these possibilities emerge from taking our best theories seriously and trying to apply them to the biggest questions we can ask. What we do know, what we can observe and measure, is that our universe in its current form began 13.8 billion years ago. It was incredibly hot and dense. It expanded through cosmic inflation. It cooled, forming the first atoms. It remained dark for hundreds of millions of years. Then the first stars ignited, creating heavy elements and seeding space with the raw materials for planets and life. Galaxies formed and grew and merged, building up the cosmic web we see today. Within those galaxies, stars continued their cycle of birth and death, generation after generation, enriching the cosmos with chemical complexity. And on at least one planet, orbiting an ordinary star in an unremarkable galaxy, something extraordinary happened. Life emerged. And over billions of years, that life evolved into beings capable of looking up at the stars and wondering how it all began. That's us. We are the universe's way of knowing itself. We are matter and energy arranged in just the right way to be conscious, to be aware, to contemplate our own existence and origins. We are the product of 13.8 billion years of cosmic evolution, a chain of events stretching from the Big Bang through the formation of stars and galaxies and planets, through the origin of life and the long path of evolution to this moment, to you, here, now, listening to this story. Every atom in your body has a history. The hydrogen in your water was created in the Big Bang. The carbon in your cells was forged in the core of a star that lived and died before the sun was born. The iron in your blood was created in a supernova explosion. The calcium in your bones, the oxygen you breathe, the nitrogen in your DNA, all of it was made in stars and scattered across space when those stars died. You were made of stardust. That's not just a poetic phrase. It's a literal truth. You are the descendant of stars, a collection of atoms that have journeyed across billions of years of cosmic time to come together as you. And as you lie here, relaxed and peaceful, drifting towards sleep, feel that connection. Feel your place in the vast cosmic story. You are not separate from the universe. You are part of it. You are a temporary pattern in the flow of matter and energy, a brief organization of atoms into consciousness. But while you exist, you are the universe experiencing itself. The Big Bang set all of this in motion. That first moment of creation, whatever its ultimate cause or origin, led inevitably to this moment, to stars and galaxies, to planets and life, to consciousness and wonder, to you contemplating the beginning of everything. Your breathing is slow and steady now. Your body is relaxed, heavy, sinking into comfortable rest. The universe began 13.8 billion years ago, and here you are, a product of that beginning, a child of the cosmos, made of ancient starlight and quantum fields. Tomorrow the sun will rise, powered by the same nuclear fusion that lit the first stars in the cosmic dawn. You'll wake and go about your day, living your life, making your choices. But somewhere in the back of your mind, you'll carry this knowledge. You'll remember that you're part of something vast, something ancient, something wonderful. You're not just in the universe. You are the universe, a small part of it that's become aware of itself, looking back across billions of years and asking how it all began. And in asking that question and seeking to understand, you fulfill perhaps the deepest purpose that matter and energy have discovered in their long cosmic journey. The purpose of knowing, of understanding, of marveling at existence. The universe is still expanding, still evolving, still creating. Dark energy pushes galaxies apart. Stars are born and die. Planets form and perhaps give rise to life. And throughout it all, the cosmos continues the work it began 13.8 billion years ago, the work of becoming more complex, more interesting, more aware. You are part of that work. Your life, your thoughts, your consciousness, these are some of the most remarkable things the universe has produced. From the simplest beginnings, from pure energy and the laws of physics, the cosmos has created you. A being capable of looking back at the beginning and understanding, at least in part, how you came to be. So rest now. Let go of the questions. Let go of the wondering. Just be here, now, a pattern of consciousness in the cosmic flow, connected to everything that is, was, or ever will be. You are home. You have always been home, because home is the universe itself, and you are made of it, part of it, one with it. The universe began, and in beginning it set in motion a chain of events that led to you. Sleep well, cosmic traveler. Dream of stars being born and galaxies forming. Dream of the Big Bang and the long journey from that first moment to now. And know that you are precious, unique, irreplaceable. A brief flicker of consciousness in an ancient cosmos. But while you burn, you are the universe's way of knowing how beautiful it is. Good night. Rest in the knowledge that you are stardust, that you are the cosmos contemplating itself. The universe cradles you as you sleep, the same universe that birthed you, that made you, that gave you the gift of existence and awareness. Close your eyes, breathe deeply, and drift into dreams, into the soft darkness of rest, carried gently by the knowledge that you belong here, that you are part of the grandest story ever told, the story of how the universe began and how it became aware of itself through you. Sleep now, child of stars. The cosmos holds you safely. You are home. Our story ends here. If you're still awake and would like to stay with us in future content, don't forget to subscribe to the channel. And if it's already late, I simply wish you a peaceful night's sleep. The brown noise you're about to hear is a low-frequency, steady sound designed to help calm your mind and relax you as you sleep. Good night.